remote umpire, the TV umpires, well, you'll be abused. So 0.3 second of imaging. What's the time required to integrate our camera pixel? We're giving 50 milliseconds. Remember yesterday we said 1 millisecond of reset and 49 millisecond of integration. That's still smaller than 0.3 seconds. So you need fast camera but not terribly fast camera either. Of course, if you want to do really slow motion tracking, people who are of my generation would remember even those days in TV we had the slow motion television. We didn't have fast camera but we still had slow motion. What other application would you need fast cameras?
Space research.
Space research.
Movies.
Where?
And stars.
Stars move very slowly. They move very slowly. I mean, their slowness is even slower than our first year bachelor students. I mean, they take 1 billion years to do something. Right?
Filming
So,
fight scenes.
fight scenes? That's not actually not a bad answer. Anyone remembers Matrix, the first movie?
Yes.
The bullet shot. But that required high-speed camera to image. Okay? And this might immediately tell you where what would be the other application of high-speed cameras.
Wild photography.
Sorry?
Wild photography.
Which photograph?
Wildlife.
Wildlife, birds don't move very fast unless you are taking picture of cheetah. And we took a very nice picture the other day of birds in our hostel area. Right? Come on, I told you something there which was moving in that scene. Our hero was moving in Matrix. There was something else moving in that scene. You guys are trying to remember which. I am old. Matrix is of my generation. Not watched the Matrix movie? The scene has been copied in n number of Telugu and Hindi movies. You know, when the hero tries to duck. What else moves in that scene? Why does the hero has to duck? What is he trying to duck from?
Bullet.
Bullet! That was the answer. Bullet moves very fast. What else moves? Now you are going in the right direction. What are things which move very fast?
Missiles.
Most of defense things move very fast.
Missiles.
So high-speed cameras are needed quite a lot in defense applications. And this is why I can't talk to you about that. Because I am coming from European Union, where we have export control to India, and vice versa. Whatever work India would be doing on high-speed camera will not go elsewhere. But that is a big market. The big market being, say India makes a rocket, it cannot buy high-speed cameras to go in the rocket. So if you guys design a high-speed camera, you have an immediate customer here. Okay? Actually, many years ago, we were asked to see if we could design one, but the export control restricted us from telling you how to design it. But scientifically speaking, how many people go about doing this is rather than putting an ADC per column, you go and put an ADC per pixel. Now you can immediately start imagining that's not a good idea. You're make diodes big and now you're putting a whole ADC in. But there are commercial products, defense products there in the market which do this trick. Now till now I have been doing a cursory take on how to design these ADCs. Just to frighten you a little bit. This is the one ADC from Levsky's work. So it's not always fairly simple design. It's not a very complex design either. If you look deeper into it, I'm not going to explain this to you, but what you can say is that's my sample and hold. There is a switch, there is a capacitor to hold. This is my comparator circuit. You can see there is a kind of a differential amplifier here. There is a remote cascode circuit which has come here. These are current mirrors. There is a golden cascode. Okay. So it's a two-stage comparator. So it's not a tricky design. And on this side we have got, there are some of the subtraction circuit. Remember, we have to do this subtraction between two signals. We had the reset and the bottom. We want to do that subtraction in the ADC as well if possible. So we have some more circuitry. So it very soon becomes something like 120 or 200 transistors. And in this we are not even showing you the SRAM pixels, SRAMs which go in. So if I have 8 bits, I need 8 SRAMs to store the data value. Each SRAM will be 6 transistors, so you already have 48 transistors just for memory. Okay. I cannot put a DRAM here, it will not be advisable, so we all go with SRAMs. And so the column pixel circuitry often takes longer to design. Okay. Good. Any question on the circuit aspect of it? I'm going a little bit faster today compared to our first few days, because I have realized it's already the third day and you guys are still looking at history. So, okay, if that is the case, I'll do a very quick summary of the next thing which we will be doing in the lab, which will be drawing the layout of the pixel. So our pixel is fairly bog standard, it's a 3 transistor with a diode. Here is one typical layout of the same circuitry. I mean, this is with a transfer gate. You do not have a transfer gate in the UMC process, you will not be doing that. But here we have tried to arrange the source follower, the row select switch in one line, reset here. So we tried to put all the transistor circuitry on one side and we have got it out. Now the reason is, you cannot draw metal lines closer than a certain minimum dimension in a CMOS process. Remember, we can only make 180 nanometer, that's the smallest size we can make, which means the smallest separation also has to be that, and often it's bigger. So if you're running long metal lines, for example, say here you're running a row select across all the pixel, VDD is running across all the pixel, reset is running all across the pixel. Wherever these metal lines are running, you have to leave some gap, and you cannot have diode below that gap. So now, here is a question for you. That is a fairly compact pixel design. What percentage of the pixel is diode according to you? Give me a rough approximation. And this the professors can also answer. 60%? So, this is where the square law comes to haunt us. Say the pixel was 2 micron or 5 micron by 5 micron. The area will be 25 micron square. If my diode goes till 3 units here, 3 micron, the diode becomes 3 by 3, okay, I have pushed it here, but if it was 3 by 3, it will be 9 micron square. What percentage of 25 is 9? You guys should be written entrance exams. You should know what's 9 divided by 25. 36%. So what looks like a 60% diode coverage very soon starts looking very bad. That's one of the first problems which we have in pixel design. A lot of area goes into the subsidiary circuit, even though they are just 3 circuits. The other thing which we have to do, we have to give some separation between 2 pixels, or else the diodes will merge. So the gap then also wastes space. This advantage which the human eye has. There is no gap between the pixels. So this ratio is called the fill factor of a pixel. What's the sensitive diode area versus what's the total area of the pixel? So an aim of pixel designer is to maximize it as much as possible. And there is a challenge you guys have in your lab. Give me as much of fill factor as possible. There are some other tricks which we apply here. Is we know this lenses can help us point the light. So in many of the advanced cameras, we have a big lens on top, but then we have a tiny micro lens sitting on top of each pixel. And the role of this micro lens is that pixel does not have quite a lot of non-useful area. Is to direct light straight onto the photosensitivity. The other thing which happened was our market kept on asking for more and more pixel. So we started with 4 transistors per pixel. We then asked the question, things like the reset transistor. Let me go back to my pixel P. You see this reset transistor, once it has reset, once it switches on to reset the pixel, then it switches off. It does nothing for the rest of the time. Agreed? Even the source follower and row select is only used when I am reading the pixel out. The rest of the time, while the pixel is integrating, the diode is working, these are switched off, they are doing absolutely nothing. So the question then comes, can we reuse them in another pixel? Can we use them for a neighboring pixel? This is where the concept of pixel sharing starts coming in place. So I have got 4 diodes here, each with their own transfer gate. Transfer gate acts as a switch. These 3 are shared between these 4 pixels. Okay. So I first reset this diode, let it integrate, then I reset this diode, let it integrate, then I reset the 3rd diode and 4th diode and so on and so forth. So now how many transistors are there per pixel? So I started with 4 transistors per pixel. 3 of them I'm sharing between 4 transistors. So how many transistors are there per pixel? 3 divided by 4 is, I'm not teaching my son's primary class, am I? 3 divided by 4 is 0.75. So essentially this comes out as 1.75 pixel transistor per pixel. And you will see such papers written very fancifully when they will be saying 1.75 or 1.5 transistor per pixel camera. Which looks very strange. How can you have a 0.75 transistor? But so here we are sharing it between 4. Had we shared between 8, our transistor count per pixel would have gone even lower. Now by sharing this circuit, this part of the circuit with the neighboring, the individual fill factor will enhance it. So the optical efficiency. Okay?
Limitation on number of transistors.
So to some extent the limitation is, so if I have 4 pixels on one side, so I have a pixel here, and a pixel here, then they all 4 can share this circuitry, or else you have to run a long wire from this central circuitry to the pixel. And that you don't want to run because you've got a very small amount of photo charge which have been generated. You don't want to move it over a long distance, you will start losing. So 4 or 8 people generally don't go more than that. Good. Questions till now? If not, I will continue for this next part of the circuitry, which is more at the architecture level. What color is this pixel capturing? And you can say it's green because the diode is green in color. But yesterday we did this derivation wherein we looked at silicon captures everything from blue to red. But we want to make a color pixel. And if we just wanted black and white image, this camera is good enough. But our end customer is not happy with black and white. So how do we make color? How did the human eye make color? All of you have studied color theory in high school. What are the primary colors? Blue and green. Secondary colors? It was taught somewhere in this school, long ago. So, courtesy a scientist from the other university, we know color mixing can produce all sorts of colors. So if you take red, blue and green and mix them in different concentration, you will get other colors. The human eye also kind of does that. It has got red poles, blue poles and green poles, and we take different colored images and somehow mix them to form color in our eyes. You might have noticed I used the word scientist from the other university, so I'm an Oxford doctorate. There's another university in the world whose name which we don't take, where once a very famous guy studied. Time for a joke. We have been doing very thick theory for the whole day. So there was a guy who discovered the law of gravitation. Have you heard the story? The apple falling story, right? The apple fell down and he figured out that there is gravity. The question is not that the apple fell down. The question is, what was he doing during office hours? He was sleeping in it under a tree. Right? So either we all should be allowed to sleep under a tree during the office hours, or that university has a very poor human resource policy. They allow their professors to go out and sleep. Try using this in front of your director and see if that works. Anyway. Okay, we can have a small break. Should we have a small break? 10 minutes, okay? But we don't have that luxury in image sensor world because we don't know what kind of processor is going to process our camera output. So another advantage which nature had, there's only one processor to these output, which is this. Whereas out here, you are going to send this image to any and everyone with different kind of processing capabilities. So to produce color, we put color filters on top of the cameras. Okay. Now there are many ways to put color filter. What you could do is you could say is, okay, let's put one row of red, one row of green, one row of blue, and just repeat this cycle time and again. But if we do that, the difference between one red pixel and another red pixel is 3 pixels vertically, right? You have red, a green pixel, blue pixel, then again red pixel. There is 2 pixels in between. But on the horizontal side, every red pixel has got red pixel next to it. So it's non-uniform sampling of the scene. So we're doing a red sample of the scene, a blue sample of the scene, and a green sample, but it's non-uniform. So the pattern which is, there are quite a lot of work on different type of patterns. The pattern which has become quite popular is called the Bayer pattern, which does something like this. It has alternative rows. In one row it does green, red, green, red. In the second row it does blue, green, blue, green. And green is half shifted. To some extent it does that because the human observers are more sensitive to green. So we get more green. And here is a typical wave pattern of the 3 different filters for, say, a typical Canon camera. You can see they are not perfectly green, perfectly red, or perfectly blue. They have a peak in red, a peak in green, and a peak in blue, but they're not ideal filters. Essentially, an optical filter design is not terribly different than classical filter design. If you remember, what's the idea of a good filter? Electrical filter, what's an ideal filter? What should it look like? Sharp cutoff? Have you designed Butterworth filter, Chebyshev filter in design or not? So a good filter should have a good pass band and then a very sharp cutoff and then good elimination band. But that is difficult to design. Mathematically it becomes an impulse function and nature doesn't allow that good impulse functions for us. Now, if we do something like this and say I have got a 10 megapixel imager, what you would see is that half of that, 5 megapixel is green, a quarter, 2.5 megapixel is red, and 2.5 megapixel is blue. Now comes the next stage. How do we get color out of it? What you could do is you could consider all of this as 1 pixel. So we take the average of green, we take the red, and we take the blue. We have got red, blue, and green. We can take color out of it. But if I start assuming 4 pixels as 1, I'm essentially reducing the resolution. I started with 10 megapixel, now I have to sell it as a 2.5 megapixel camera, which is not what the market demands. So what we do in debayering is we try to extrapolate. So let's look at this red pixel. What might be the green value here? And what might be the blue value here? So one thing which you could think of, okay, this is red. On all 4 sides I have got green. If I take the average of that green, we might come out with what might have been the green value here. To some extent that works because in nature we don't have sharp boundaries. Think of this question very importantly. It comes very useful when we do compression. So look at me. Nothing is sharp in my face. Things are moving smoothly, right? There is a smooth transition. There is no sharp transition. Look at this wall. There is a sharp black line here. That rarely happens in nature. Nature does not have. So what do sharp features mean? A pulse feature means high frequency contour. Like if you do the Fourier transform, you will have all the high frequencies as well. So in nature, very rarely we get sharp features. So that's why there's low high frequency content. And hence taking average, if you're taking, of course, you might say, but professor, we're not taking pictures of nature only, we are taking pictures of real life human, inanimate objects like buildings and other things as well. True, but most of the times, we could work with some sort of relationship. Now, one relationship, of course, is you can take the average of green, and to find blue here, you can take the average of 4 blue pixels in the corner. But again, the problem lies. The green is being sampled in this way. Blue is being sampled in this way. So essentially, each color pattern is being sampled slightly differently. So it's not the same. Ideally speaking, we would like to have the same sampling to get the exact image. The other problem arises, let's look at the green centered pixel. So I want to find red here. I only have 2 reds in nearby, there's no red on top. So when I was at the red pixel, to find the green value of that pixel, I had 4 pixels to average. Here, I only have 2 red pixels to average. Am I making sense? Not making sense, stop me. Because your facial feature says that I am not making sense. By now, as a professor, I have learned to read, so stop me if it's not making sense. Okay? We'll go on the board, and that will be much nicer. Yes? No? Should I continue? Yes. Continue there, continue on the board. Board? Okay. It might have been the samosa effect as well. You know, we get carbohydrate bump. When you eat carbohydrate after not eating for a lot of time, you feel sleepy. Try that with rice. See why in afternoon lectures we feel more sleepy than morning lectures? Because in afternoon you eat rice to come to it, and morning generally is, if you're a boy, if you get to eat something, that's a good day, right? So let's look at green. If I want to find the red value here, I can take only average of these 2. If I want to find blue value here, I take the average of these 2. Green I already have there. Okay. Now if I want to come here, if I want to find the green value at this pixel, I have got 4 greens to average and 4 blues to average on the corner. So the way I am averaging out is not uniform. So as a result, I get a bit of noise in the image. Now this is an area of quite a lot of work which have gone in. I mean, right these days a number of people will use some sort of a bilinear transformation of the red and green rather than just pure simple linear averages. There are also people who are using works on neural networks to debuyer an image. At this point, you might say, but Professor, my image has perfect color. So let's do this as an exercise. What would be the most colorful thing in Warangal? Where should we go and get color image? Is there a temple which have where the walls, the Gopuram has been color painted? Thousand Pillai is very bland, right? We are looking at a new temple where the Gopuram they paint with multiple colors. Is there something like that here? Bhadrakali, is it color painted? No, we have never been to Bhadrakali, or the exams are not nearby. People only remember the gods when the exams are coming by, right? If not, there are some trees with flowers outside, bright red flowers and green trees in the background. When you guys go out and there will be a yellow background, the building background will be behind that. All of you try to take pictures. I'll put a web page where you can upload those, and then we will look at the color constancy in different pictures. We'll just display them here and see if they all look the same. Do you think they all will look the same? They might. Maybe your phones are all designed by the same company. It's possible. If all of you have got the same branded phone, they will look the same. But if they are having cameras differently, you will see a different color reproduction. So rather than taking my word for it, let's all take a picture someday and bring it tomorrow or day after. I'll create a web page. Actually, you know what? The shared folder which I showed yesterday will keep it for you to upload things. So let's look how color constancy appears. So to some extent, it's an exercise of how you do debugging, of course, how good the color filters are. This debugging technique would have worked brilliantly if my color filter was blue, jup, and then green started here, went up, and came down. Now, most of these filters are some sort of a polymer filter which are deposited post-chip fabrication. So once the chip has been made, we then put a pattern of lenses, micro lenses, and a pattern of color filters. Okay. Good. So we're now in the realm of image system design. I'm not going too much into circuit design. Now let us look at some of the problems with this design. One problem which we already showed yesterday when you try to take a picture of the thing up there, which was the dynamic range problem. So the problem looks something like this. That's a picture of McGill University taken by me. So if you take low intensity, you can see the features in the sky, but you don't see any features in the building. Right? If you integrate for long, you see the features in the building, but you don't see anything in the background. And you might have seen similar problems with your images which you have taken. I mean, in the Western world, I often ask people to take a picture in a dark nightclub, but knowing Warangal, nightclubs and Warangal don't go together, right? So I don't know where you can. Oh yes, just try to take a picture of a bright sunny day, which we get 364 days of a year, while standing below a tree, and try to take the whole background. So the sunny sky, tree, and somebody standing below that, and see if you can get the contrast, how well it works. So that's one problem. And the other problem which we have is that of a rolling shutter. This is an image I took at, I think it was at Guwahati airport, wherein the old planes when things start moving faster. And I have taken in both things too. I mean, you could possibly try also taking pictures of your fan. Yeah, that's a good idea. You all have fan in your houses. We have a fan here, but we already have high. Should we try taking a picture of the fan? Problem is these are big wings and the fan is moving fast. Okay, lunch break, we try to find a room which has a ceiling fan. The reason being because these fans also have these lines, and in case your camera does not have high resolution, these lines will look like uniform thing. I'm sure there is a room with a ceiling fan in this building. So we can start knocking at doors of people. Professor has asked to take a picture and see whoever has. Move it at speed of 1, 2, 3, 4, 5 and try to take pictures of this. you will see at some point of time, the wings of the fan will start bending. And the reason that happens is because of the problem of rolling shutter. Remember, when we are taking an image, we read one row. And in one row, we start from the first column. We convert to digital, take the output, convert to digital, take the output. By the time we have reached the last row, we had assumed the scene has not moved. But if the scene starts moving, so here in this case, these wings, they moved, and you can see what has happened. We have got this shearing pattern here. Same here. This is the same, it's just a wing or rotor of a plane. And you can see this wing would have been here, but I started reading from here. By the time I reached here, that wing had come down here. So it looks these image deformation are happening because of the rolling shutter problem. Our human eye does a global shutter. It shuts, takes a picture. The old mechanical, reel-based cameras were also like that. You had a shutter, you take a picture. Our shutter is now each pixel gets reset one at a time. We read a row, we reset the row. We read the row, we reset the row. We read the row, reset the row. So we are doing a rolling shutter problem. Okay? So let's try to find some solutions to the first problem, because we realized at least one of you had a very good camera phone yesterday where you did not get this problem. And maybe the lady who had a wonderful phone, could you try taking a picture of this scene up and see how it works today? Actually, even when we look at this, the scene starts getting saturated. Have we? Try looking up here. And you will see very soon it will start becoming very brighty. Try taking a picture. Let's see how your phones work here. So we're just taking picture of this scene, the dark area around this and the light source. All of you, I think you have mobile phones, right? You don't have mobile phones? So who can see a picture which looks as good as their human eye? I will come and look at your pictures then. I'm tired sitting here. I need to come and trouble you guys. Oopsie. Ooh, civil engineers don't like us. Show me the pictures which you have. Okay, so you have lost all resolution here, right? It has become one big blob. It has become one big blob. Oh, it's actually not too bad. One big blob in between. You can't see the individual columns, right? Many of you will not be able to see the grills. Can you see the grills? The human eye can see the grill, right? Even those of you who are wearing glasses, you can still see that. Still cannot see the grills, right? I can just see. That's perfectly fine. What about you guys? Anyone has got a good fancy camera? Still looks like a white blob. What about you all?
The same problem that
Oh, you are having a good camera, but the background is completely darkened. So you see, this is a very good example here. Keep both of them here. Show me. So your phone, look, this is a very good reaction. So his phone decided to concentrate on background. So the foreground, this white has become completely blobbered. Your white is good, but your background is gone. We'll show you why this problem happens in a minute. But that is a very good example. Actually, can you upload if I give you the access to my, you are all are on Google of some sort, right? So I'll just show that web page again. Can you upload these two pictures? What about you guys? That's also a good example of that thing. But the background is gone. Good camera. Decent camera works? The photographer has a good camera. Well done. Why is that not surprising? What about you guys? Now, decent work. Okay. But the background is lost now, right? What about here? You can take a good image, but the background is lost. His background is there, but the foreground is lost now. Right? He can see the background, but this is completely gone. Okay, so I'll share that web page. Why don't we show these two images to everyone? Okay. So I can show you my own pictures, or you guys can trust the pictures taken by your friends. So ooh, where did that go? Just give me a wee second. Let me